Hello everyone, myself Dr. Rovin Kumar, Assistant Professor Department of BCA, IIMT College of Management, Greater Noida. Today I am going to give online lecture on group theory. Before starting, I am giving your brief introduction on topic of group theory. Group theory is a part of pure mathematics. It has important role in UG, PG, IIT JAM, CSIR NET, or other exams. First topic, set. A set is a well-defined collection of all distinct objects. For example, set of natural number, set of real number, set of integers. Binary operation, an operation that contains two elements of a set, giving another elements of the same set, is called a binary composition or binary operation. Generally, a binary operation can be represented use dot or star. Group. G be a non-empty set and star with a binary operation. G star is called the group. It satisfies the following properties. First property, closure property. Closure property for AB belongs to G, A star B belongs to G. Second property, associative law. A star B star C is equal to A star B star C. For all ABC belongs to C. Third property, existence of identity. A belongs to G, then there exists B belongs to G such that A star E is equal to E star A is equal to A. Fourth property, existence of inverse. A belongs to G, then there exists an element B belongs to G such that A star B is equal to B star A is equal to E. Group theory, exams and proof. G is a group such that AB belongs to G, then AB inverse is equal to B inverse A inverse. To prove A dot B inverse dot A inverse is equal to identity. Where I is the identity element of G, consider the left hand side of our equation. We have left hand side is equal to A dot B inverse dot A inverse, A dot B into B inverse dot A inverse. B into B inverse is equal to identity. Under associative law, A dot I dot A inverse by associative law, A B into B inverse is equal to identity and A into A inverse is equal to identity. And A dot I is equal to A. A dot I dot A inverse. A dot I is equal to A. A dot A inverse by identity law is equal to I. By identity law is equal to RHS. If in a group G, second exams, A, B, and C are the three elements such that A dot B is equal to C dot B, then A is equal to C. Proof. Let us assume that A dot B is equal to C dot B. Equation first. Since B is an element of a group G, this implies there exists some B inverse in G with identity element I, such that B into B inverse is equal to I. Equation second. On multiply on both sides, equation first by B inverse, we get A dot B into B inverse is equal to C dot B into B inverse. A dot B into B inverse is equal to C dot B into B inverse by associative law. From equation second, B into B inverse is equal to identity. A dot I is equal to C dot I. A dot I is equal to A and C dot I is equal to C. So A is equal to C by identity. Exams. This is also known as the right cancellation law. For example, set of integers under addition is a group, where Z is the set of integers. First property, closure property. For AB belongs to G, then A plus B belongs to G. For example, 1 belongs to Z and 2 belongs to Z. 1 plus 2 is equal to 3. 3 belongs to Z. Second property, associative law. A plus B plus C is equal to A plus B plus C. Left hand side is equal to right hand side. A, B, C belongs to Z. A is equal to 1, B is equal to 2, C is equal to 3. Left hand side, A, 1 plus 2 plus 3. So 1 plus 5 is equal to 6. Right hand side, 1 plus 2, 3 plus 4. 3 plus 3 is equal to 6. Left hand side is equal to right hand side. Existence of identity. A belongs to G. So then there exists an element 0 belongs to G. A plus 0 is equal to 0 plus A. Under addition identity 0 and under multiplication identity 1. Existence of inverse. A belongs to G. Then there exists an element B belongs to G. A plus B is equal to B plus A is equal to identity. Identity is equal to 0. Where B is equal to minus A is the inverse element of A. A minus A is equal to 0. 0 is the under addition identity. Or minus A is the inverse of A. Order of group. Number of elements present in the group is called the order of the group. That is the cardinality. It is noted by G cardinality. Order of elements. Order of elements. Let if A is the of finite order, then the least positive integer such that an is equal to E is called the order of A and is denoted by order of A. The order of a group. Find order of each element of a group. G is equal to 1, 2, 3, 4. Under multiplication modulo, 5 is a group. Order of element, order of 1. 1 to the power 1 is equal to 1. Order of 1 is equal to 1. A to the power n is equal to identity. Order of element 2. 2 to the power 1 is equal to 2. 2 to the power 2 is equal to 4. 2 to the power 3 is equal to 8. Divide by under multiplication modulo remainder 3. 2 to the power 4 is equal to 8. Divide by under multiplication modulo 5 is equal to remainder 1. Order of 2 is equal to 4. 3 to power 1 is equal to 3. 3 to power 2 is equal to 9. Divide by 5 remainder 4. 3 to power 3 is equal to 27. Divide by under multiplication modulo 5 is the remainder 2. 3 to power 4 is equal to 81. Divide by 5 remainder 1. Order of 3 is equal to 4. 4 to the power 1 is equal to 4. 4 to the power 2 is equal to 16. 16 divided by 5 remainder 1. Order of 4 is equal to 2. Subgroup. A non-empty subset H of a group G is a subgroup of G if H is a group under binary operation star of G. We use the notation H subgroup of G to indicate that H is a subgroup of G. For a subset H of a group G, then H is a subgroup of G. If H is not equal to 5, if AB belongs to H, then AB belongs to H. If A belongs to H, then A inverse belongs to H. Abelian group. G be a non-empty set, star be a binary operation. It satisfies the following properties. First property, closure property. AB belongs to G, A star B belongs to G. Second property, associative law. A star B star C is equal to A star B star C. For all A, B, C belongs to G. Extents of identity. A belongs to G, then there exists an elements A belongs to G. A star E is equal to E star A. Extents of inverse. A belongs to G, then there exists an element B belongs to G. A star B is equal to B star A is equal to identity. Commutative law. For any element A belongs to A, B belongs to G. A star B is equal to B star B. G is called a abelian group. cyclic group. A group G is called a cyclic group if there exists an element A belongs to G such that is every element of G can be expressed some integral power of A. A is called the generator of G such that G is equal to A की power n such that n belongs to Z. Examples: multiplication group 1 omega square formed by the cube root of the unity is a cyclic group generated by omega square. The multiplication group 1 minus 1 iota or minus iota formed by the fourth root of the unity is a cyclic group generated by iota minus iota. Normal subgroup. A subgroup H of a group G is called a normal subgroup of G if for every H belongs to G and H belongs to H. That is X inverse belongs to H for all X belongs to G. Notation: if H is a normal subgroup of G, then we denote if H normal subgroup of G. Every subgroup of index 2 is normal. Properties of normal subgroup. If H normal subgroup G and K is a subgroup of G such that H subset K, then H normal subgroup of K. Second, let K be the normal subgroup of G and H be a normal subgroup of K such that H subset K, K subset G. Then H need not be a normal subgroup of G. Both G and H are normal subgroup of their direct product G cross H. Point 4. If H is an index to subgroup of G, then H is a normal subgroup of G. Point 5. If H1 and H2 are two normal subgroup of G1 and G2, then the direct product H1 cross H2 is a normal subgroup of G1 cross G2. Properties of cyclic group. A cyclic group is generated by A, then it is also generated by A inverse. Every cyclic group is abelian. A cyclic group is generated by A, then both the order of G and order of A are the same. Let G be a finite group of order n. If G is a cycle, then there exists an element A in G such that the order of A is n. Every subgroup of a cyclic group is also cyclic. If an infinite cyclic group G is generated by A, then A and A inverse are the only generator of G. Group homomorphism. A mapping F such that G to G dash between two groups G and G dash is called a group homomorphism if FA dot B is equal to FA star FB for all AB belongs to G. Example of group homomorphism. The following is an example of a group homomorphism. The mapping F such that Z under addition to Z under addition defined by Fn is equal to 2n for all n belongs to Z. Fn is equal to 2n for all n belongs to Z is a group homomorphism because Fn1 plus n2 is equal to 2n1 plus n2 is equal to 2n1 plus 2n2 is equal to Fn1 plus Fn2 for all n1 n2 belongs to Z. Properties of group homomorphism. A 1-to-1 group homomorphism is called a monomorphism. An onto group homomorphism is called an epimorphism. A group homomorphism is called an isomorphism if it is both 1-to-1 and onto. An isomorphism from a group G onto itself is an automorphism. Thank you.